Good morning. So we were going to learn today steady state cornering of two-axle vehicle. So already we have done pure cornering and its governing equation we derived. And pure cornering of vehicle in a curved path is dictated by 2 degrees of freedom. One is its lateral velocity motion response. Another one is its yaw velocity response. And we were able to have two single degree freedom set of equation for a bicycle model for this pure cornering study in the last class. And we were importantly deduced that two equation in the form of state space equation, which are very quite useful equation when you have to have a control strategies for your vehicle in order to have vehicle controlled motion, intended motion. If that is that matter, you want to go in for anti-lock brake system or active control system for cruise control, any control strategies that are going to be involved in your vehicle. You see that vehicle parameters and the required motion to be governed and controlled by your control system design should essentially look at the governing equation of motion. And those equations are represented in the form of state space equation set, and you would see the wonders take place, and then you would be able to come out with the appropriate algorithms and the control design. And what is in short to say the advantage of state space system is you would be able to describe your vehicle characteristic with the help of a matrix called the state matrix. So that's essentially is what you have looked at in the last class. You see that was this. So we had our equation derived, and at the end we have brought into this equation form. And here you see this A matrix is what is called the state matrix, and that state matrix can be determined with the help of vehicle parameters, mass, rotational mass moment of inertia, I, Z, Z, and then you see the tire cornering stiffness values, and then geometrical aspects of your vehicle, small a and small b, and then your forward speed. So these all are the data if you know for your vehicle, and you know what is the state matrix of your vehicle. If you have state matrix in your hand, you would be able to comment on the characteristic of your vehicle during a mid and high speed cornering. So that's essentially what today we are going to look at with an important governing equation for simplified on the safe motion of vehicle expected called the steady state motion. And we are going to define an important parameter called understeer gradient. And with the help of this understeer gradient and fundamental equation of motion for steady state motion, we would be able to do classical comparison of vehicle characteristics of group of vehicles which are available in the market. So that is what is the beauty of this part, and today you are going to learn what is called the steady state motion of your vehicle. So I'm just going to show this today's class lecture number 21, steady state cornering. And in the last class, what we have seen kind of from the bicycle model description of your vehicle, this equation number 1, which is delta F is equal to L by R minus alpha F plus alpha R, where this alpha F and alpha R are the slip angles in the front and the rear axle respectively. And your pure cornering governing equation is now reduced to one single equation, as steady state motion of a vehicle is described by time invariant parameters. That means your response, yaw velocity and lateral velocities are constant. That's why you have only this equation sufficient to do. Then we ask the question that, then what is that fundamental governing equation? Is it not accelerating? Yes, of course. The motion is changing from 1D to 2D. You require an accelerated motion, and that acceleration is your lateral acceleration. So we have studied in your basic engineering mechanics course curvilinear motion. I just recollect that that would be a very nice point for you to start with. So look at if this is the path of your vehicle motion, and you have your vehicle going in this the velocity v, and its acceleration is generally represented on the curvature side. We have its acceleration something like that, and that acceleration can be resolved into two components. One is this AT component, sorry, AN component, and the other one is along this, that is AT component. So when you have your acceleration is like that, you see this, that the velocity is not going to be constant, that would be dictated by this AT component, and it will be varying. But in case of a steady state motion, for steady state motion, you require this velocity is constant. The velocity here, it's not the small v, don't misunderstand. So this is velocity of your vehicle, that's constant. And when that can be constant, when AT is 0. That means what? The acceleration, total acceleration is now is only AN. So only AN would be there, which is now, as per the vehicle, it is lateral acceleration. How is this lateral acceleration is obtained? That is A, that's velocity square by the radius, so the turning radius r. So this is what we have looked at as a lateral acceleration. So when this lateral acceleration is there and you have to do its dynamic equation, you would have this lateral acceleration is what is responsible for its motion and its directional behavior, and which is also for dynamic equilibrium require cause of your centrifugal force, right? So that's all which you have already studied, where this x-axis and this y-axis represent the path. This is path of your vehicle motion, and the vehicle here is considered to be a particle. Geometry of the vehicle is neglected. So you understood what is steady state motion. Only when AN is present and AT is 0, and that motion is what is steady state motion. And then the directional response is what we are studying. Now, in our vehicle dynamics, we do not consider the particle ideology. So we'll look at a real vehicle, and that vehicle is what is our bicycle model. So when you look at your bicycle model, this is your bicycle model. When it is given some steering input during your mid or high speed cornering duration, we are not talking about low speed cornering, correct? It is mid or high speed cornering. At that time, you see that you have your forces here. As we have already seen, these angles are a smaller angle, so we can consider this FYR and FYR. And these forces are developed at the tire contact patch in order to have a necessary lateral acceleration to be developed at the CG location of your vehicle. And in a dynamic equilibrium, you see that you would have this is balanced by a force called the centrifugal force. So what is your centrifugal force? So that force would be mass times, so in mass would be weight by G times U squared by R, U squared by R. So this is your centrifugal force and these two. So this is what is your free body diagram, FBD, during dynamic equilibrium. During dynamic equilibrium. So this is what is centrifugal force. If I have to apply Newton's law, this is going to be what is going to act in this direction because of these two forces. I am applying D'Alembert's equation. So what is D'Alembert's equation? Sigma F Y plus this, that is W by G U squared by R. is what is equal to 0. So this is the equation that we have. So sigma Fy is what? Fy F plus Fy R, that's equal to W U squared by GR, right? That's equal to W squared by GR. So this is what is your requirement of equation. So now, as we have already looked at your tire lateral force in a single tire is developed is because of slip angle, right? So the variation of your slip angle is going to be limited by your road adhesion limit. And we have seen that the slope at this point O 0 is what is defining C alpha all. So this Fy is given by C alpha times alpha, right? That's what we have seen. So if that is so, I can replace this FIF by minus C alpha F into alpha F minus C alpha R into alpha R. That's equal to mu squared by, sorry, mu squared by R W U squared by G into R. G into R. Now I have to substitute here alpha F and alpha R. See, you understand why this minus sign here? So here FIF and FIR are positive and this is negative because of SAE coordinate system. So what is your SAE coordinate system? At this CG location, this forward direction X, lateral direction in this Y, and Z direction represented like that. It is down. So this is the convention. So these are the axis set. So these two are positive here, whereas this is when I add it's negative and that goes on this side. So this is our equation. And I'm replacing my FIF and FIR by these two values. So now I can further simplify this equation, finding out this alpha F and alpha R. So how do I do that? For that, I'm just going to take moment. So let's call this point as A and this point is B, contact point. And taking moment about point B, I'll get FIF. So that's going to be FIF, and that's a positive moment because of right hand row of moment. And about B, it will create positive moment that's positive into L, because this wheelbase length L, and that's with the minus W by G U squared by R into B, because this distance is B, this distance is A, so into B, and this minus is because this is going to be with respect to coordinate system, consider it's negative moment, and this is what is going to be equal to 0, and I would be able to get from this my C alpha F. So here if I substitute FIF as minus C alpha F into alpha F L, and this is going to be on the other side WB into U squared by G into R, and I can now write what is my alpha F this way. So alpha F would be WB by L, and this is C alpha F, right? This is C alpha F, and that's coming. That minus sign also will come here, and this by 1 by C alpha F into U squared by GR. So this is going to be what now? See, WB by L is what? WB by L. If I look at my vehicle, So this is my WF, and this is my WR. This is my total weight at CG. and this distance is A, this distance is B. A, this distance is B. So now WF into L is what is equal to W into B, and that gives me WF will be WB by L, and WR will be equal to this simple moment equation in mechanics. We have that in rigid body mechanics, WA by L, right? So I can replace this WB by L by the load at the front axle minus WF by C alpha F into U squared by GR is what is my alpha F. Similar way, taking moment. So this equation, how do I get? Taking moment about point B equating to 0, considering clockwise moment positive with respect to the convention I have got. Similarly, if I do taking moment about point A and equating that to 0, I would be able to have now alpha R equals minus WF. Here WF become WR now by C alpha R into U squared by GR. Right? So substituting these two into one. So let's say this is equation 1 and 2. Put in Roman letter 1. What do I have is delta F equals L by R minus alpha F. If I substitute this minus of minus become plus. So plus and U squared by GR is both the term I take out. So it will be WF by C alpha F minus WR by C alpha R. Within bracket, outside is going to be U squared by GR. Right? So now this term is what is very interesting. This term is what is defined as Understeer gradient or the Understeer. Sorry, this is slipping. My stylus pen, I have to change the needle, I think. Do that Understeer gradient. Understeer gradient. And WF by C alpha F is what is called a tire compliance. So WF by C alpha F or WR by C alpha R. So the load in the front axle divided by the cornering stiffness, combined cornering stiffness of both the wheel, right? C alpha F. This is what is called a tire compliance. Tire compliance. Compliance is something reciprocal of stiffness. So you see this 1 by C alpha F. C alpha is stiffness, so it's reciprocal term. That's why the term compliance comes and the tire compliance. So when the front axle wheel tire compliance are greater than the rear axle wheel tire compliance, you get this KUS value positive, right? Positive. At that time, the vehicle tendency is called the understeer tendency. If they are equal, both the compliance, then KUS becomes 0. If it is on the other hand, if WF by C alpha F is smaller than that of WR by C alpha R, that is front tire compliance is smaller than that of the rear tire compliance, then you get your understeer gradient value negative, that is less than 0, and that is going to be inducing in a vehicle called an oversteer tendency. So these physical insights we are going to understand. Before that, let me just rewrite this equation, this form. Delta F is equal to L by R plus KUS into U squared by GR. And this equation is what is called the fundamental governing equation of fundamental governing equation of steady state motion. Steady state fundamental thermal equation of steady state motion. So let's call this equation now as equation number. What was the Roman letter earlier? We had 4 up to. I think this is equation 5, but that will have 5. So now, what is this equation says? The steering angle requirement for your passenger car is going to be function of the geometry of your vehicle, L. It's going to be function of what is the turning radius that you are going to take a turn. Not only that, it's also going to be function of your forward speed as well as understeer gradient. So when you say understeer gradient, it is again going to be a function of tire stiffness, cornering stiffness, and the load on that. So it is like more of dependencies are there, right? And this understeer gradient, understeer coefficient called is very, very vital. And that is what we are going to now take it further to understand some physical insights of this. Right, if you look at it's very complex. The cornering stiffness, if you look at, it's going to be function of the inflation pressure of your tire. It's going to be function of what is the normal load that they are acting on your tire, and it is also going to be function of tractive or braking effort or lateral force that are acting on this. So it's all when we are going to look at tire dynamics, we look at the cornering properties of tire, and we'll learn more requirement of tire properties for handling. At that time, more of the understanding would be there. Time being, please remember that this KUS depend on many of the vehicle parameters as well as an operating condition of your vehicle. Right. So let's now look at some physical insight of this steady state motion with the help of understeer gradient. So what am I going to do? I'm going to draw a graph where I'm going to take this steering angle requirement in vertical axis, and in the horizontal axis I'm going to take speed of my vehicle, because you see explicitly it is depending on the speed and it is u square. So if you look at the steering wheel requirement is now function of square of your forward square velocity. So let's have first case, case 1. When this KUS equals 0, what do you mean by that? That means you would have alpha F is equal to alpha R, or you would say tire compliances WF by C alpha F equals WR by C alpha R, right? C alpha R. So this tendency is what is called neutral. Neutral steer condition or neutral steer tendency of the vehicle. Tendency. Neutral steer tendency of the vehicle. So when KUS is 0 in this, it's going to be only L by R. So what is the L? It's wheelbase. That's not going to change. What is R for a steady state motion? You are going to go in a constant radius, if you consider, of say 30 meters. Let's take for this vehicle model, L is equal to 3 meters and R 30 meters. So if that is so, L by R is what? 0.1 radians. So this is in, sorry, my stylus is not supporting today. 0.1 is all in radians. And you see that's going to be represented by a constant value. This is neutral steer tendency. And my steering requirement is constant for the increase of speed, for the increase of forward speed. What I mean by that, let's look at now the actual path, the circular path. Trying to represent that circular path here of the turning radius R 30 meters here given, right? And I have my vehicle now over here, represented by this bicycle model, right? Its motion would be now, if it is neutral steer vehicle, it is along the curve. Path will be along the curve. So what does that mean? So if suppose the driver accelerates his vehicle, when it's acceleration, there is the traction comes. We said there will be an influence of traction in your C alpha F, and that is going to be changing this understeer gradient and so on. But take granted that for time being, I would say acceleration means there are tests on the constant radius. Yes, so first lap will be of particular speed, say 60 kilometers per hour. Next lap will be 65, 70. Like that, they keep increasing the steering in the test. It's not increasing the steering, increasing the speed in the test. That is how, if it is incremental way, if I change the speed, you see that the requirement of your steering angle is not changing and the radius is constant. So this is your neutral steer tendency. That's what you should interpret as physically. When your vehicle is having your front and rear tire compliances are same, you have understeer gradient 0, and it is the requirement of steering, irrespective of the speed and a constant radius path, is going to be sufficient for its negotiating the curve. Now on the other case, let's look at case 2, where understeer gradient is positive. Case 2. As KUS is greater than 0, then what would happen? You look at, since that is function of velocity square, the variation of requirement of your steering angle is parabolically increasing. So let's consider corresponding to the double the steering here, whatever that you have. So neutral steer effect is what? It is simply L by R. And here, if it is corresponding to 2L by R, the speed here, whatever that you have, that speed is called the characteristic speed of your vehicle. We'll see what is it. Characteristic speed of the vehicle. Right? This is going to be having or representing your understeer tendency of the vehicle. So what do you mean physically here? If the vehicle front tire compliance is greater than that of the rear tire compliance, the slip angle at the tire contact patch in the front is greater than that of the rear developed, you would see that for the given steering angle, as you increase the speed, the turning radius would be increasing. So your turning radius is no more constant. That's going to be increasing. I will represent that like this. So if this is the intended radius, your vehicle would go in this. So you see there is a turning radius increase. Or to have the constant given turning radius, I have to maintain this course. I have to increase my steering angle. So from here, the steering angle is increased, and that is varying parabolically as it is function of U square. So that is what physically you look at it. So my vehicle is understeer vehicle. So when can I call my vehicle as understeer vehicle? If it is front engine mount and front wheel driven vehicle, you see that most of the load on the front axle. So your vehicle tendency would behave like an understeer effect, right? At that time, if we are going on a vehicle in a curved path, a circular track, and you have to accelerate, what would happen? The turning radius would increase. To correct that, you have to give a steering input. And then that's what is the requirement variation here. So you see that steering increases as the speed increases. So that what is called an understeer tendency of the vehicle. It's safe. You can give a steering and do it. On the other hand, case 3. So what is this case 2? It is an understeer vehicle. So it's called an understeer tendency. Case 3, you can have your KUS less than 0. When can it happen? When the slip angle developed at the rear of the tire is greater than that of the front tire rod interaction. Then you would see this KUS is going to be negative, less than 0. And that time, this vehicle tendency is called, or vehicle characteristic condition called oversteer condition. Oversteer condition. So the requirement of steering angle would be now different. So what will happen if a vehicle is having oversteer behavior, its KVS is negative, what will happen? That vehicle would travel in a path when you are trying to drive your vehicle on the constant radius path, the radius of turn would be decreasing. So this is what is going to be the path, oversteer effect. So see, you could see physically the turning radius decreases. With the given steering input, then we go. Correct? So what does that you require? What does that is meaning? If your vehicle is a oversteer vehicle, your steering requirement as you are accelerating your vehicle in a car would be decreasing. So what do you mean by decreasing? When I drive my vehicle, I would be trying to decrease my steering angle instead of increasing. When I have to take a right turn and I'm accelerating, my vehicle is a oversteer vehicle. When it can happen if my vehicle is a rear engine mounted rear wheel drive vehicle. It's an example of your oversteer tendency vehicle where Americans prefer this vehicle. We'll see that. So at that time, what would happen? You would have to reduce the steering. And you could have witnessed in racing of your vehicle, the race cars are designed for to have an oversteer condition as it is going to vary with the lateral acceleration. You see that whenever the racers are taking a turn, sharp turn, they are going to instead of steering on the turn side, they will counter steer. That means they would reduce the steer to get onto the course. So that's what is happening. So if a vehicle is oversteer vehicle, the turning radius for the given, if you fix your steering angle, that is going to be reduces. I have to have my path maintained, then I have to reduce my steering angle, right? So that is the meaning of oversteer tendency. So this can be looked at like a vehicle on a physical circular path, or I can even look at my vehicle which is going in a straight line, straight motion. So what is my vehicle? Like that, right? This is my vehicle, originally traveling in straight. My rear wheels. This is my front wheel. The vehicle, if this goes, and this is my CG location, when can I have my this tendencies? How can I explain for a vehicle which is going in a straight path? If this vehicle in highway goes with mid or high speeds, and then I have all of a sudden a wind gust is acting in this direction, there is a side force. You have seen that when side force acts, you see the wheel travel direction would be not along the longitudinal direction. It is at an angle. That's where the slip angle is manifested. The slip angle also manifested whenever you give a steering input. But when you go straight and when slip angle comes into the tires, when there is a side force acting and that side force is responsible for that, so you would have slip angle at the front as well as rear. If that happens to be same, like case one, you see that your vehicle would go rather in a straight path at an angle. That is what is body slip angle dictating. So this is the path of your vehicle and during neutral steer, neutral steer in a straight path, it will be like this. Supposing case to understeer vehicle, your vehicle is a understeer vehicle and this is going to act here, that would initiate what an alpha F greater in the front than rear. So the steer slip angle developed in the front is greater than that of the slip angle developed at the rear. So what would happen? That's going to give a yaw moment generated and that make your vehicle to turn on the side of the disturbance. So your vehicle would go in this way, and that is your understeer tendency. Because here you have slip angle more than this, and then what will happen? The drifting of front wheel will be there compared to that of rear wheel, and your vehicle motion would be in this direction. It will go. On the other hand, if your vehicle is a oversteered vehicle, what will happen? The front of the tire slip angle alpha f smaller than this, so the resultant lateral force would make rear drifting, and this is not, because you have alpha f smaller than alpha r condition for oversteer condition. At that time, your vehicle would be coming inward. So this is my side force. My vehicle, instead of going straight, it would be turning on the side of my disturbance. That's oversteer tendency. So that is how you can describe your physical vehicle behavior. And to describe that physical behavior, what is needed is this understeer gradient. So this understeer gradient now can dictate your characteristic speed as well as the critical speed. So what is preferred in your vehicle is an oversteered is not preferred. Why? Because that would take your vehicle to an unstable state. So the directional stability would become question mark beyond certain lateral acceleration, beyond certain speed of your vehicle called critical speed. Your vehicle cannot be controllable. The steering control will be lost. See, look at here. There is a speed as I accelerate my vehicle on a curve, and the vehicle is behaving as oversteer tendency. KES is negative. What will happen? The speed decreases. At one point, the requirement of steering angle becomes zero, and that speed correspondingly called a critical speed. Beyond that speed, your vehicle directional stability is a question mark. So your vehicle can be designed for oversteer condition, but the driven speed of your vehicle should never to go beyond the speed. So that's what is it. So what is the speeds? These two speeds. So what is that? First, for the characteristic speed, what is the condition? If the steering requirement is double that of what is required for the neutral steering effect, that's 2L by R is what is equal to L by R plus KUS into AY by G. AY is U squared by R. So in this now, this L by R here, 2L by R that goes. So what is my KUS? I require my speed. So this AY is what is U squared by R. So my U would be given by under root of GL by KUS. GL by KUS. Similarly, what is my critical speed? My critical speed to get, what I should do was the steering angle is, when it is zero, I'd get my critical speed. So on this side of my equation, if it is zero, that's L by R plus KUS into U squared by RG, G into R. Zero, so this goes on that side. So I would have my velocity critical. Critical is going to be under root of GL by minus KUS. Minus KUS. So you can see inside the radical is minus. So for an oversteered vehicle, KUS value is negative. So negative goes for plus. And G times the wheelbase by this value, what you get from the tire compliance values, you would be able to get the critical speed of your vehicle. Till then, the stability of your vehicle will be manageable, controllable by counter steering, right? Otherwise, you would not be able to do. So we have defined now two speeds. One is characteristic speeds, UCH. Another one is critical speed, the UCR. So I'd stop at this point of time, this lecture, and we will continue with this with some example and what is something called a handling diagram requirement in the next class, right? So this is what is steady state motion that helps you to understand three important driving tendency of your vehicle or handling characteristic of your vehicle called neutral steer tendency, understeer tendency, and oversteer tendency. Understeer tendency is preferred always for a safe drive. Oversteer tendency is preferred for a thrill and sporty vehicle. So SUVs, if you look at, they are very closer to neutral steer, and the other side of maybe it will have some oversteer condition for the thrill. But any sedan class, any passenger car is designed for an understeer condition, so that you would always have a safe drive. You don't need to worry about critical speed and so on. So, and this is what we will see in more detail in again upcoming classes. If you have any doubts in this derivation of fundamental governing equation of steady state motion and the physical insight and the three characteristics of your vehicle during cornering, mid or high speed cornering. If you have doubts, I'll explain further. Otherwise, we will end the lecture today. Hope you have followed today's lecture and it was interesting, right? Any doubts? If no doubts, I'll stop recording.